So hello everyone. Today we're doing another authoritative problem, which is called different divisors. We gave you an integer d and asked you to find the smallest byte integer a, so that a has at least four divisors, and difference between any two divisors of a is at least d. Okay, so basically it's saying that this problem that a has at least four divisors, and the difference between any of the four, like any divisor, is at least d, right? So difference between any two divisors at least d, right? It says that um, we have to find the smallest integer a. So we have to find the smallest a which satisfies these both conditions. Of course, if a number has more number of divisors, um, suppose a number has three divisors and a number has five divisors, and of course this number would be greater than this number, right? This makes sense, or it's not always true, but if a number satisfies both these conditions, then I guess like that should be true because only it is only possible if a number is prime. Suppose 17 and 8. It has more number of divisors than this, but it is less than this. But if a number has a four divisors, right, at least four divisors, and if it has more number of divisors than that, then that would be greater than this number, right? So with that approach, we should find the numbers which only has four divisors and try to conclude to an answer. So from my assumption, let's model it like this. A must have a divisor as 1 and A itself, right? And there are only two places left, which we have to think and fill. So let's think about a representation of A, how we can represent A. So A can be represented as multiple of prime factors, right? Like prime factorization, as we say. So it can be represented like this, right? Where pi is a prime number and alpha I is whole number, right? So any number can be represented like this using prime numbers, and the number of divisor it has can be written as in this function, right? So using the knowledge of this, we conclude that a number which has like let's try and like try to fill these both places by a single prime number, right? So if that number is suppose that prime number be p, then its power should be 3 in order for factors to be equal to 4, right? So the given factors would be like this: p1, p square, and pq, right? These are the given factors. Else, the position can be filled like this: p, q, and p into q. If p and q both are prime numbers, right? And one of these would be less than equal to square root of n, or a, we can say, right? So using this knowledge, um, we can write the factors like this. Now from this, we know that the difference between the least of two should be greater than equal to d, right? So p minus 1 should be greater than equal to d. So p can be written as d plus 1. And similarly, after seeing this condition, we should compare these two, and we will find out that q minus p should also be at least greater than equal to d, right? So then q would be equal to d plus greater than equal to d plus p, right? And now using binary search, we can implement and try to find the value of p in the prime numbers, and similarly the value of q. And now let's try to code this up, and I think we're approaching it in a correct way. So then put in the value of D. Then we will build a prime array. Let's name it primes. We'll use C, of course. Right. We make 0 as true. What's my bad? And now we'll iterate from when I equals to 2 and then is prime is prime dot I will iterate from, let's use long here, and equals to I into G less than equals to n, G is equals to I, right? Is prime dot G equals to 4. Yeah, let's try to test this. And 0, 1, 2, 3, 4, 5, 6, 7. And let's try to run it one time only until 20. Nineteen, right? I think it's correct. 2, 3, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, I think this is correct. And so we can push it also. If is prime, primes dot push back I, right? Now let's tell this, and I equals to less than I plus plus CO times dot I. Nothing. Yeah, now I think it's correct. For the primes we have, yep. It's working perfectly. Now we just have to search on the lower bound for P, right? and then p equals to, I think we should take int only. P equals to bound of primes dot begin x dot end or d plus 1 at int q is equals to lower bound of primes dot begin. So we're basically binary searching over the values to find this, to find the minimal p and minimal q. And yeah, and then see out minimum of, I think this would exceed, right? If we multiplied 3 times, so we should use long p, 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 comma, and then p into q. Now, okay, let's test this. Yeah, I think we have it. Let's try to submit this. Hmm. Different devices, right? TLE, and getting TLE. Hmm. Anything wrong? Let's take a value of n a bit smaller. Around 25,000 would be also fine. Right. Now let's try to submit this. Let's check the solution if this works or not. Yeah, this got accepted. Although this solution of mine was a bit different, which I had tried on that situation. This was completely by my own approach. So yeah, it was really a good problem. From my perspective, I think it's more rated than 1,000. But yeah, still very good problem.